Okay, well, thank you very much to Matthew and for inviting me to come along to this. I gave a talk this morning about our best attempts to understand the Big Bang and what happened at the Big Bang. And also I was trying to explain why this has become more and more important. So this slide here shows everything we learned about fundamental physics in the 20th century. Okay, so on the top right of the diagram, who knows who that is? Anyone know who that is? That's the person who understood how 3/4 of the particles in the universe work, and his name's Paul Dirac. And he gets 90 of the known particles in the universe. There are up, down, charms, strange, top, bottom, then electrons, muons, tauons, the neutrinos, and they have colors and flavors and so on. You add them all up, there are 90 of them, and they all obey his equation. It's a remarkably simple, unique equation, which he discovered, and it describes 3/4 of the world. Does anyone know who the guy on the bottom is? This is not a scientific audience. That's James Clerk Maxwell. James Clerk Maxwell understood how electromagnetism works in the middle of the 19th century, wrote down very simple, beautiful equations which describe everything like light, radio waves, X-rays, all forms of radiation obey his equation. And building on Maxwell's work, people developed the theory of the strong force, the weak force, and ultimately Einstein developed the theory of the gravitational force. The achievement in understanding all the particles and forces is really one of the great achievements of humanity, that we understand the particles and forces. There are always a few things we don't understand, one of which is dark matter, where we have some models and ideas, but we don't really know what it is, as Matthew talked about, and the most mysterious is the dark energy, which was only discovered about 10 years ago, and is also quite mysterious. So the basis for cosmology is Einstein's theory of general relativity, and I can't possibly explain this, let alone explain the development of it, except heuristically. So I'm going to just do that with a picture. That the development of Einstein's theory of space and time, so basically the central intuition in Einstein's theory is that space and time are joined together in space-time. They don't exist separately. And secondly, that this is a flexible substance which can be distorted, and the distortion in space-time corresponds to the force of gravity. And there's no more profound implementation of this idea than in the universe itself. The universe is expanding, and so the space between galaxies is growing all the time. Now, M-theory has arisen out of this. It's arisen out of the attempt to connect relativity to quantum mechanics, which Matthew also talked about. And this is our best theory, which unifies all the previous particles. All of these particles and forces are all embedded within this theory called M-theory. This was only invented about 10 years ago, and the central idea in M-theory is very simple, that there are geometrical objects of different dimension. So space-time has dimension 4 because there are 3 space dimensions and 1 time. But you can have 0-dimensional objects called particles, or you can have 1-dimensional objects called strings, that's called string theory, or you can have 2-dimensional objects, membranes, or 3-dimensional objects like our world. And we often talk about our world as a brane world. Brane is short for membrane, but the joke was that if you have a dimension that's different than 2 is a membrane, you call it a p-brane. And so this is a theory for p-branes. So you have to excuse physicists for a terrible sense of humor. So in M theory, all of these objects occur, and in fact, there are not only are 3 dimensions of space, there have to be 7 additional dimensions for mathematical consistency of the whole construction. Just to give you a picture of this, a photon of light, the stuff we receive all the time in our eyes, a photon of light in this theory is a little spinning piece of string with 2 points on the end, and this thing spins around at the speed of light, and that accounts for the polarization of light. You can have right-handed or left-handed polarization according to which way the string is spinning. A graviton, that's the particle of the gravitational field, is just a doubled length of string, okay? So, and that's why it has twice the spin of a photon. So it's a very sort of geometrical and in some ways extremely naive picture, and it's quite astonishing that it does contain particles of all the types we know are there in the real world. Now, so I mentioned there are not just the 3 dimensions we're familiar with. In this theory, there are 7 extra dimensions. 6 of them are curled up in a little ball, and Matthew showed a picture of this. So at every point in this room, there is not just X, Y, Z, the 3 directions you're used to, length, height, and breadth. There's another 6 dimensions which we can't see. And the reason we can't see them is they're very small. They're curled up in a little ball, but if you had a super powerful microscope, you would discover that indeed there are extra dimensions of space. At first sight, this sounds a bit of a cop-out. I mean, why? So you can't explain the laws of physics, so you invent all these other dimensions. That's not really the way it works. It's a rewriting of the problem. It turns out that the configuration of these extra dimensions actually does determine all the laws of physics that we see. So if you want to explain why is there electromagnetism, strong force and the weak force, why are all the particles we see, it's because the 6 extra dimensions are curled up in this particular way, and you can understand that in great detail mathematically. Of course, it makes it much more important to understand what happened at the Bang, because the place where the configuration of the extra dimensions was fixed was at the Bang. So in this way, particle physics has just become a branch of cosmology over the last 5 years. We're all talking about the same problem. What happened at the Bang? How did things get fixed the way they are? Now, the 7th dimension of space is even more bizarre in this theory. It ends on 2 branes. And so these branes are special branes. They're like mirrors. They're also called the end-of-the-world branes. There is no space beyond these branes. There are 2 of them, and one idea is that the matter we're made of lives on one of the branes, and the dark matter, which we can't see with light, but we can see with gravity, that lives on the other brane. And I want to show you a model we came up with. Paul Steinhardt is my collaborator at Princeton, and so we developed a model for the Big Bang, a mathematical model to describe what happened at the Big Bang based on this idea of branes. So in our model, you start with 2 flat, empty branes. They attract each other and collide. They fill with radiation and matter. They expand along their own dimension. The ripples that were present when they collided turn into galaxies and stars, and eventually the expansion of the universe dilutes them away to nothing. Dark energy is very important in this model. The dark energy is really the energy of empty space. It's the energy of these branes. And the dark energy it has a repulsive gravity, and it causes the universe to expand after the Bang and dilute away. So in our future, the universe will be entirely dominated by dark energy, but that energy is nothing but the energy of attraction between the 2 branes. And so eventually it will pull them together. The dark energy will in fact decay and convert into radiation and matter that fill the universe. So this model was very surprising because it's a cyclic universe. It's not a universe which began 14 billion years ago. And in fact, nobody has ever really explained how something can begin without a cause. And that was always the assumption behind the standard model of cosmology. So people were quite shocked when we developed a mathematical model without a beginning. It's quite hard to stop a cyclic universe. Okay. So I want to end by talking about something which Matthew discussed, which is an idea of holography. Now, this is this was a theoretical idea developed about 10 years ago in the context of M-theory, and which recently we've started to apply to the cosmos, to cosmology. And I want to explain one thing about it, which will connect, I hope, very well with what Matthew said. You see, I've explained a geometrical picture of the world, Einstein's theory of space-time as a smooth, flexible substance, and now this has been generalized to strings and branes and particles which interact with each other. That's geometry. Okay? How does quantum theory link with that? And this is how holography comes in. This idea of holography, which was the person who came up with it was an Argentinian physicist called Maldacena. What he showed is that if I have a universe, literally I have a universe, a region of space-time where gravity is important. Okay, so inside the space-time you can form galaxies, matter can collapse to make black holes, you can have gravitational waves, all of the phenomena of gravity. So I've got this universe. Now consider the boundary of that region. That means the surface of that region of space-time. On that surface, you can put some theory on the surface, okay? And what he showed is that actually, whatever the theory of gravity is in the bulk, we call it the bulk, that's the interior of the space. Whatever the theory of gravity is, there is what's called a dual theory on the surface. So this dual theory is completely equivalent to the theory in the bulk. You can describe everything in either picture, just whichever one you use is a matter of convenience. They're completely equivalent. And the bizarre thing is that the theory on the boundary, or the surface, doesn't have any gravity at all. So in that sense, gravity is an illusion. And in these theories, gravity can always be described using the surface theory. What's essential in the surface theory is it's a quantum theory. You cannot describe anything in the surface theory without, it's very quantum. So this was an amazing development, and recently we've been using it to understand how you go through the singularity in cosmology. That if you have a region of space-time, there's collapse towards a singularity. Einstein's theory fails at that point. Okay, everything goes wrong. You get infinities, the density typically becomes infinite, and so on. But if you can understand this surface theory, the holographic dual, then in the holographic dual, you can follow the universe right past the singularity. And once you're past it, you can perform this holographic map into the bulk again and predict everything that happens. So these sound like very woolly and spacey ideas, but I can assure you they're not. They're very precise and very mathematical. Of course, they're only speculations. We don't know if they're right or wrong, but what we get out of this are predictions as to what the next important observation will be. And I talked a little bit about this in the morning, that the next frontier for understanding the universe is gravitational waves. If we can measure gravitational waves coming out of the Big Bang, we can look right back and see what happened there, and all these ideas are actually testable. So thanks very much.
Could I ask you just to speak about one more thing, which is the idea of scale invariance?
Okay.
I'm just asking Neil to talk about one thing that's particularly relevant to this structure, because one of the things we came across, which Ben and Chris are about to talk about, so you guys should come up, is the fact that as we made a certain kind of structure that could build across any space, it generated its own internal rules, which meant that it had specific and very fixed sets of scalar relationships. And this relates to Neil and Paul's theories in a very particular way to do with the idea of how the universe. So we've got this thing he's talked about, the membranes come together, there's another Big Bang. Now you might think, as I did, that means that the universe is sort of reset back to very, very small. But that's not what happens at all. Nothing changes. The atoms don't all suddenly get really, really small again like the Incredible Shrinking Man, and then get really big and then come back again. The atoms all stay the same size. The quantity of matter in the universe increases in each cycle. And a space that is very, very small now, perhaps the size of this model, will grow in the next cycle of the universe to be as large as the entire universe, and so on for. Now I'm going to hand it back to you to actually explain how that really works.
Oops. Is this still turned on? Yeah. Yes, this phenomenon of scale invariance is one of the sort of fundamental notions in cosmology. Okay, and I want to show you a real picture of scale invariance. In fact, it's this one. So this is our best picture of the universe.
That's all right, it's not on anymore.
Oh, it's not on.
We're unplugged. Well, I'll hold it up for you.
Oh, sorry, they've just unplugged me. I didn't spot them.
Here we go.
I didn't spot them unplugging me.
This one, for those of you who can't see, this one is much more blobby than this one.
So basically what the observations show is that if you look at the universe on the largest observable scale, okay, right across what we call the horizon, which Matthew talked about, the entire light travel distance since the Big Bang, that's 14 billion light years. If you look at the universe on that scale, the density of it varies by about 1 part in 100,000 from this side of the universe to that side. They're different, but only by 1 part in 100,000. Now you go to a smaller length scale, half the length scale, you go to 7 billion light years. It's still, the differences from place to place are still 1 part in 100,000. Now you go down to 7 meters, okay, in the early universe. The difference is still 1 part in 100,000 from place to place. So that's called scale invariance. It means that the pattern of distortion of the universe is independent of scale. And that is an observational fact about the universe we see. What's particularly beautiful about these theories of repeating Big Bangs is they are inherently scale invariant. So when I take this picture of gravity in the bulk and describing space-time, and I map it to its holographic dual, the defining property of the holographic dual theory is that it's scale invariant. And so there is no scale. And that means that in that theory, in a sense, the only result you can get out of it is scale invariance. It's really built into the framework. So some of us regard this as very tantalizing. There is a link, there's a potential link between the deepest property of gravity, namely that it's dual to a theory that doesn't have any gravity, and the explanation of scale invariance in the universe. So this is all, new research. As I said, it's on the cutting edge. We're not sure it's all going to work out as we would like it to, but I think I think what Matthew's trying to do in putting this into something concrete and visualizable is very helpful, not just for the scientists, because we like to have any help we can get with visualizing what we're doing is great, but it helps everyone appreciate that we've made enormous strides in understanding how the universe works, and there is nothing more beautiful than the universe. And I think representations of it like this are very, very important and exciting. So, thanks.
Thanks.
Thank you. Hello?
Oh, can I borrow this for 1 second? I just want to, there's a reason this project's called The Morning Line, which is, you'll keep seeing these flashing up. The Morning Line, for those of you that like gambling, is a betting newspaper. Tells you all the horses of the day. But it's also an idea of the beginning of the universe, every dawn is the morning light. Like, and at the beginning of the universe, there was a very particular moment where, you could first see. It's when the first photons are released from the plasma. So it's it's trying to get you back from this kind of this idea that the whole thing is a massive gamble.
Thanks, Richie. We just wanted to say thank you to the Serpentine Gallery, to Julia Peyton-Jones and her staff, to Ulrich Obrist, Olafur Eliasson. My name is Benjamin Aranda. This is my partner, Chris Lasch. Our firm's called Aranda Lasch. It's in New York City. We're deeply grateful to TBA, to Francesca von Habsburg and Daniela Zeiman for formulating this radical commission, and of course to Matthew Ritchie. As you can tell from his talk, it's been intense and very rewarding, and it's actually an amazing kind of collaborative structure to be a part of. Chris and I are going to talk, and we're going to focus on the geometry and the structure of the morning line, which we developed with Daniel Bozia from Arup's Advanced Geometry Unit and Nicholas Sterling. What you are looking at here is a drawing. The drawing is made from many drawings which build a three-dimensional space, and this space can be inhabited. All these drawings connect together to form one large picture. And this picture acts as a metaphor and a model of a cosmology. It is a conception of the universe rendered through Matthew's drawings. What is fascinating to us as architects working with Matthew is that he challenged us to use, let's say, the mundane aspects of our physical reality, things like wood, aluminum, steel, paint, structure, and gravity, to use these things and represent an event, something like, say, the Big Bang or many bangs, and use basically the things of our world to describe what really constructed our world, like the Big Bang and its aftermath. So, and in this case, as Neil Turek's been talking about, he was interested in the cyclical model of the universe. So our just to clarify, our role as architects in this project was to build a framework for Matthew's drawing to accomplish this. So what the project started, we went to a lecture Matthew was giving at the Gramercy Arts Club in New York, and as you'd heard from Matthew's discussion, there were two thoughts that we really walked away with, two sentences, and they are that the drawing is a bit of information, and the universe is a kind of picture. And we really liked these statements because they were something that, as architects, we could break down in order to build up a project out of. The bit can maybe be something like an element or a shape that can build a drawing, and the drawings can maybe build a picture, and the picture can be of the universe. So the first question that we were confronted with is what kind of a universe are we dealing with? And as Neil's been talking about for both his talks, Neil's partner, co-author in the Endless Universe is Paul Steinhardt, who we've had a few meetings with in New York and discussions with. And this is from an email. I'm just going to read it, basically clarifying for us as a team kind of how our model is working with this conception, this sort of cosmology. And that is that every volume of empty space that is a few centimeters apart today will occupy a 14 billion light-year universe and be filled with galaxies and stars one cycle from now.
So the project really begins with the bit. The bit is the atomic the atomic unit of the project, and it's that shape there. And Daniel Bozio was instrumental in helping us to concoct and develop this shape. Every element in our framework is made up of this one shape. It's a truncated tetrahedron, which just means it's a tetrahedron with the corners lopped off. And it's a shape that has a couple special properties. We knew that in order to be a useful model of expansion, the kind of expansion and acceleration that dark energy is driving in the universe, that the bit would have to scale. So you'll notice that the truncations aren't exactly symmetrical. There are short edges and there are long edges. And what this affords the bit is the ability to scale in a fractal manner. It's a kind of Sierpinski scaling where the bit can scale down at a ratio of 1 to 0.375 and then up at a ratio of 1 to 2.66, so that it's this kind of endless, it's capable of this kind of endless growth or endless enfolding onto itself. So we know that the bit needs to account for all the space of the universe, but it also needs to account for the matter that's in it. And matter, we know, is made through networks, and it's made through lattices. So our bit, through a very simple set of rotations, can rotate, mirror, scale to create a network, which is really a set of interlocking rings. And more than that, then this network can tile into a lattice. So it's sets of rings that connect with other sets of rings to make a kind of endless cycle that expands in 3 dimensions. And we wanted to use these properties of the bit, scaling and expansion, networks and matter, to create a kind of picture, which is really the design of the project. And what we're aiming for was to create our own kind of cyclical model. And it begins with these two poles, these two states, these two branes, kind of ordinary matter on one side, dark matter on the other. And it also serves to organize the site, in that it locates the two main programmatic elements of the work, a video pavilion on the right here, and the amphitheater, the performance space, on the left. You can consider this the kind of the first generation in the fractal scaling. The second generation grows off of the triangular faces of these first generations, and the third generations grow off from that. And I've said that the bit can scale a network, but it can also scale through networks. In other words, there's a potential network around every one of these bits that exists one scale down. So by completing the second generation, we create these rings, which serves as the main structure of the site, creating these vaults and these arches that carry the load around the programmatic spaces and down to the ground. The third generation is grown in some places, and then the whole structure is coded in order to map a narrative onto the kind of generic geometric structure, and that's something that we'll talk about later on. So this forms our cyclical model for the project. It's these two networks revolving around these two poles with a twist in the middle that connect them.
It's on. The bit is a framework for drawing on. Next. It contains certain rules, and as long as we follow these rules, we can always be certain that the drawing connects to other drawings and that the drawing can scale. So you can see the drawing actually on the bit here. And if you just follow the rules of the bit and how it grows, the drawing grows as well. The overlapping narrative that determines all the different drawings, if you see the model, there's a kind of shift of the drawing type that moves from one end of the pavilion, the anti-pavilion, to the other. On one side, the character of the shift is highly crystalline and triangular in nature, and on the other side, it's very chaotic and sort of loopy, loops within loops. So what you have here, this model just shows you kind of both things happening at once. It's the framework or the geometry with the drawings mapped onto them on the site. And for us, it's been fascinating as architects to deal with this issue. I think it strikes to the heart of collaboration with an artist. It's this issue between, say, framework and geometry and expression and drawing, or as Matthew was describing earlier, content and moment, or information and causality, or what's being described as an intrinsic structure. Just to wrap things up, this three-dimensional network that you saw, the model, we flattened it to become this map that you see on this white part. So you see the little three-dimensional model up on the right. And this map is a kind of common description. It's like a composition or a score that of the project that is then shared with other collaborators that Matthew's brought in, musicians and performers, and they interpret this map and make it their own and produce their own work out of it. This is the building of the model, which anticipates how one would build through modularity. Again, all these pieces are the same, so there's a kind of highly modular build out to this thing. And just a couple of final images of the model here on the table. You can see the performance space, the video pavilion. Again, moving from this shift from a sort of crystalline type drawing to a chaotic one. And you can see these horizon lines that kind of carry through the picture in a way, slicing it in all these dimensions. And okay, absolutely. Sorry. Well, just a word about the material. I mean, we're thinking of a lightweight composite, aluminum foam, possibly with steel. Matthew challenged us to basically materialize a structure through darkness, which is quite a challenge. So this shiny black paint that you see in the model has a significance to his previous work and this one. And just to finish up, Chris and I wondered where this came from, and it's easy to say that maybe this shiny black paint can represent, say, the dark energy that Neil was describing as this kind of expansive entity that has taken over the universe, something, as he said, that's repulsive in nature. But we know now with Matthew that that could be one explanation, maybe not, but there's always definitely more.
Thank you, thank you. So we've got one final experiment. Thanks, Ben. We just have one more thing to do, and then you can all go home and rest your tired brains. Just remember, when you get that sense that there's too much stuff going on, that's actually your brain superheating as the it's trying to process the information, which is the physicalized form of, I've got to plug this back in, of information itself. Because if we grant that information is physical, then it has to have a physical manifestation to appear in your head, which is why your head gets hot, because of all the friction of all the information going through it. So it's a totally legitimate expression of thermodynamics. So we're going to have one last experiment, which is, we've talked about how we made this and why we made this, but it does one more thing, which is it's actually supposed to work as a storytelling machine. It's designed to be the representation of both all of these theories and facts, which are our time, but also to relate them back to all of the origin points. And that map Ben and Chris showed is not just a kind of game to be played. It does a number of things. It relates through, with a certain degree of allowance for a little bit of slack, through every religious system that's been evolved in the West and used in the Western world. Every musical system, the chromatic scale can be used to go through it, or the circle of fifths, for example. It's like a wheel. It doesn't have an inherent story. It's an investigation machine. The other thing, we're just going to need to turn that projector back on again. It seems to have gone off. So I'm just going to very quickly show you, we have an experiment here. It's an experiment which has seemed fitting to close the marathon with, and it's an experiment in presentational technology. In other words, I brought as many little gadgets as possible that don't talk to each other. We're going to see if we can get them working. This thing here, this is a model of how the projection work. It's mirrored inside. And the idea is that if you can create a projected space, like the one Neil was talking about, a holographic space that on its surface contains all of the information that is contained in the interior, maybe, just maybe, you can go inside it with this camera and see what it's like to be extrinsic to our world. In other words, we're the projection on that surface, and we're going to go in and see what it's like if you could get off our surface. It's that famous experiment done in the 19th century called Flatland, where they talk about how do you explain 3 dimensions to a 2-dimensional person. And this, for me, goes back to the question that I asked Joseph Quigley yesterday, which was, he was saying, well, how do you teach a monkey to fish? Well, the answer, for those of you that weren't here, was, well, first it will need a fishing license. And so that's a big conceptual barrier for the monkey right there. Even if it does, technically it's able to drop a line in the water and pull it along, and the fish grabs it and the monkey pulls it out. It's not fishing until it's got the fishing license. So to get off our plane is a context question that's far more sophisticated than just sort of poking our head up. You have to actually redefine the context of what is permitted for the monkey to fish. The monkey requires permissions, and you has to understand the entire set of circumstances. And that's how you get off the brain into the bulk. So we're going to have a look at this and see what we can see. We have to agree to all kinds of contracts with Apple, apparently, to turn this on. And then we're going to try and explain how you read it, possibly, through this structure, how the structure becomes a story. As Ben and Chris were talking about it, I'll just sort of wander around this model here. It moves from a crystalline structure, which is the beginning of the universe, which you're sort of familiar with the... Am I double mic'd? No, that's okay. With the great idea, this is this thermodynamic spread. And the idea, as we build it, is that we're going to sort of add more and more parts. The whole thing is a sort of modular structure that can be rebuilt in different ways on different sites. So it contains within itself the potential to tell more and different stories each time it's told. But the story that we're first talking about is the story of Paradise Lost. So as you move through the structure, there'll be a score that plays that tells you various fragments of a sort of reimagined Paradise Lost, because the story of Paradise Lost is very remarkable in literature in that it is several stories all told from completely different points of view. But you don't really get that when you first read it. It sounds like you're sort of hearing this great familiar tale of the universe, bad Satan, good God, questionable Adam and Eve, possibly naive. But then the more you read it, the more it becomes clear that it's actually a retelling from several different points of view, all of which are in utter disagreement about the very fundamental nature of the universe itself. They're not saying that they've come to some sort of agreement. They've actually got profound disagreements about even who's in charge, who was supposed to be in charge, how it all began, how it all ended. The Paradise Lost ends with Adam being shown a vision of the future, of the flooded world, which is sort of remarkable given that Al Gore just got the Nobel Peace Prize for just pointing out exactly the same thing. but the world sort of like vanishes, and this is like it's kind of a vision of entropy, and it's implied that this is somehow his fault, but that's only because it's being shown by an agent of one particular side of the argument. On the other side of the argument, you still have Satan. He's still in hell, which is an infinite place of infinite. It's unclear whether it's entropic or static, and it's also very unclear whether Milton admires Satan, because he's writing at a time where there's this political dimension about who is in authority, how authority should be challenged. And what's kind of fantastic is, as a metaphor, or even potentially an analogy, is he talks about it, the light of hell being not light but darkness visible. So this was one of the very first sort of poetic ideas of this structure, being actually a materialization, a slice of the universe. Do we have the... Okay, here we go. We're close. I don't think you need one, just go continue. Yeah, you really don't need one. You just need to go to where it says view, or up there. No, you've got the old one, right? All right, just keep going. See what you can do. Maybe we can turn this on and broadcast to the world. But perhaps there we go. This is just as good. If we have a very small, tiny camera that we can put inside. No. The idea is that you'll sort of see as this. All the internal walls of this are reflective. So when you're inside it, it becomes a kaleidoscope, showing you the structure and meaning of the universe. That's right. As it goes, and it's a story. And as you walk around it, it will change by the nature of the participation of the people involved. Brilliant. Here we go. So here we go. We're going to put the camera inside. This will be you. Technical fault. So, it's obviously, this is a very crude representation, but every direction inside the space reflects the narrative that you're seeing, which is a sort of way of trying to physically describe the question that is so problematic for a physicist like Neil, which is like, where do you stand to see everything? If you're a part of it, how do we define the difference between ourselves? So it's taking those two things I talked about earlier, the linear drawing, which encases, in a way, is drawn on the surface of reality. So it's all a bit blurry. This is an experiment. And the recursive space of language and of quantum space, these two kinds of systems at the same time, and letting them all come together and seeing how that can be a representation of the Big Bang. And then the other, that's probably just going to give everyone a headache if we leave it on too long. The other thing I'd like to show very quickly is just a short map of how it works as a... that's not the one. Maybe it's this one. Well, since probably fitting this ends on a sort of fictional note, you'll have to take my word for it. But the footprint that Ben and Chris showed you, that drawing that turns into a map, can be read as a load diagram for engineering. It can be read as a musical score. It can be read as a... No. Don't worry about it. It's just, it'll take too long. Or it can be read as a story. And the story is our story. So the ideal is, this is an experiment very much, this structure is still in progress, still very much part of this collaboration, is that each person comes and brings their theory to it, brings their information. Like everything that's happened here that I've seen becomes part of this. And the more we get into it, the more we'll be able to change it and adapt it. It's actually designed to be adaptable and changed. It's unlike buildings. And this, in a way, could be proposed as an experimental model of how we will think of buildings in the future. They're not fixed. They're not a thermodynamic narrative that, of course, we know. I mean, I've worked on a number of public projects, and you're told at the start, this is a 50-year building. In 50 years, it will have to be completely stripped down and rehabilitated. We're not talking about stereotectonic buildings for centuries. We're not talking about Chartres Cathedral. We've already accelerated long past that point, but now we're in a position of kind of terrible waste. So we have to all start thinking about what will everything become, because everything becomes something. And build that kind of superposition of states, that kind of quantum uncertainty, and allow for it, like in a sense encourage it into every structure, so that in the future we can look at these things and say, well, you know, of course they didn't exactly know what this could be, because it could be anything. They gave us this gift, and then now we're allowed to change it. In fact, it's intended to accept and build on change. So I don't know if anyone has any questions for Neil, Ben, or Chris, if they're still around, about the way this is going to work. Otherwise, I think we can hand it over to Julia, if she wants to say a few words and wrap it up. And thank you all, and Hans Ulrich for coming.